This project will attempt to protect an elderly family member from predatory robocallers and telephone spammers using a networked call blocking system with custom wireless caller ID displays. My videos are fast-paced, but all the code, notes, and images are posted on my website. MicroPython will be used for the software. Specifically, sockets will be used to sniff network broadcast packets, hardware timers will be used to interrupt program execution, an OLED library will be used to display custom fonts, and contact data will be loaded from flash storage. Before starting this project, I tried Nomorobo and a popular hardware call blocker, but neither helped. Many unwanted calls are from cons who constantly spoof their caller ID. Finding a solution has been challenging because the octogenarian is a true Luddite. She refuses to own a smartphone or a computer and has never been on the internet. This ruled out mobile and VoIP solutions. I considered open source communications software such as Asterisk, but it seemed relatively complex and not necessarily reliable. She has 20th century telephones connected to a true copper POTS line. The phone system's great in terms of reliability. The system works even if the power goes out. I tried getting her a new caller ID telephone, but she was intimidated by all the buttons and confused by the superfluous text on the low contrast LCD. My initial plan was just to build a custom caller ID module with a very easy to read OLED display that would only show the caller's name and no other text that might distract her. My first prototype also has a NeoPixel, which illuminates green or red, signaling if it's safe to answer the phone. I was going to use an HT9032D module, which is a common chip for parsing caller ID. However, I was a bit reluctant because it's probably against the law to connect any uncertified terminal equipment to the public switched telephone network. Fortunately, I found a used commercial caller ID box on eBay for $15 US. The device has all the necessary government certifications. It supports 4 lines, but I only need 1. There's a serial port which can be connected to a computer or microcontroller for monitoring or configuring the device. But what's even better is there's an Ethernet port, which broadcasts caller ID data along with a lot of other information over a local area network. This greatly simplifies the implementation and isolates anything I build from the phone company. The box requires 9V DC, but the power adapter wasn't included. One pitfall is the barrel jack needs to be negative tipped, which is less common. I cut a positive tipped power adapter and swap the positive and negative leads. Since the device is network enabled, any Wi-Fi capable microcontroller should be able to sniff the transmitted caller ID information. I selected an older WeMOS ESP32 because I have several in my junk drawer. I've used these boards in several of my previous tutorials on how to set up and write MicroPython code for the ESP32. These older boards are still available on eBay for around $5 US. They have the WROOM32 chips that don't have the additional PS RAM found in the WROVER versions. Nonetheless, they should be adequate for this simple project. The only other required component is a good quality screen. I selected a 2.42-inch monochrome OLED display with white text on a black background. OLEDs have excellent contrast, even in a sunlit room. They also have extremely wide viewing angles. The resolution is a bit low at 128 by 64, but more than adequate for large text. This 3.3V display has an SSD 1309 driver with a fast SPI interface. Therefore, it's easy to connect to the ESP32. The ground from the display is connected to a ground on the ESP32. The display's VCC is connected to a 3.3V pin on the ESP32. SCL or serial clock is connected to GPIO 14, which is the ESP32's HSPI serial clock. SDA or serial data is connected to GPIO 13, which is the HSPI MOSI. Reset is connected to GPIO 16. DC or data command is connected to GPIO 17. CS or chip select is connected to GPIO 5. I found it necessary to add a 180 microfarad capacitor between VCC and ground because the big display can stress the 3.3V supply enough to brown out the ESP32. I created a case in SketchUp to hold the OLED display and the ESP32. The micro USB jack will be accessible from a slot on the side. A hole in the bottom of the case will allow the reset button to be pressed with a paperclip. The top and bottom of the case are printed in white PLA. 4-threaded brass inserts retain the display and the cover. The other 2 inserts secure the ESP32. I soldered a right-angle female header to the ESP32 along with a 180 microfarad capacitor. 10mm tape is applied to the back to insulate the ESP32 board from the display PCB. The ESP32 fits into the bottom. The tape is peeled back to insert the screws. Two 2.5mm Torx screws retain the ESP32. Its micro USB port is accessible via the slot on the left to provide 5-volt power. A small piece of anti-static foam is placed between the two boards. The 7-pin male header on the OLED plugs into the female header on the wiring harness. The display fits into the top cover, which snaps tightly into the bottom. 4 2.5mm flathead socket screws secure the top cover and the OLED in place. I also printed 2 legs for the case. Later, double-sided tape can be applied to ensure they remain in place. Since the displays are wireless, they can be placed anywhere in the house. They don't necessarily need to be by a telephone. Also, the Wemos ESP32 has a LiPo battery charging circuit, so battery power is an option too. I went ahead and wrote a MicroPython library for the SSD1309 and posted it to GitHub. The library supports drawing lines, shapes, images, and text. The repo is very similar to my other MicroPython display libraries, such as the SSD1351 and the ILI9341, which I covered in detail in previous videos, so I won't repeat it now. Also, the repo contains many examples, and the code is well documented. In VS Code, I have a MicroPython project. There are a few fonts, the main caller ID program, a comma-delimited file of contact names and phone numbers, a lightweight FTP program created by Robert H.H., my SSD1309 OLED display library, and my XG-LCD font library. Let's take a look at the caller ID program. From select import select. This library supports monitoring platform-specific input-output operations, such as networking. From socket, import socket, which affords access to low-level networking operations, such as broadcast packets. From sys, import modules. This lets you reference loaded Python modules. From time, import sleep. From machine, import pin, SPI, and timer to control ESP32 GPIO pins, SPI interfaces, and hardware timers, respectively. From network, import WLAN and station interface to monitor the status of the Wi-Fi connection. From SSD1309, import display. This is my OLED display library. And from XGLCD font, import XGLCD font for loading and drawing fonts. Next, a few constants are defined. Port is set to 3520. This is the UDP port number that the caller ID device uses for broadcasting. Buffer size is set to 128. This is the maximum length of the broadcast packets in bytes. Display width is 128 pixels. Display delay is 60,000 milliseconds, which will display messages for a 1-minute duration on the OLED. Several constants define the caller ID data position in the broadcast message. There's data for line number, call type, incoming or outgoing, indicator for start or end a call, duration, checksum, ring count, time of the call, and of course the phone number and caller name. SPI is instantiated and set to 10 MHz on the HSPI bus. An OLED display is initialized by passing the SPI bus and the pins for DC, CS, and reset. The display is cleared. A variable WLAN is used to monitor the Wi-Fi. The actual Wi-Fi connection is established in the main.py file that runs automatically when the ESP32 boots. If the Wi-Fi connection is active, then the IP address is displayed on the screen. Otherwise, an invalid IP warning is displayed. The built-in MicroPython 8x8 font is used. A font loading notice is also displayed. 2 versions of the Pixel Perfect font are loaded, which takes a couple seconds. There's a large and a smaller version. Afterwards, the display is cleared and put to sleep to save power. A contacts DIC is defined. It'll store key pairs to associate phone numbers with contact names. A hardware timer is defined. A function called loadContacts is used to load the contacts data into the DICT. The comma-delimited file located on the ESP32 file system is opened. A loop reads the contacts until it reaches the end of the file. Any new line or return characters are stripped. The CSV data is split on the comma into phone number and contact name, and then added to the contacts DICT. The phone number is the key, and the name is the value. A function called displayNameMax is used to display text on the OLED and maximize the font size. The passed name parameter is measured using the larger font, which will be used to draw the name if the text length is less than the display width. Otherwise, the smaller font's used. A function called handleFTP allows the user to remotely enable an FTP server on the ESP32. There'll be multiple displays in the house, and This will allow updating the code or contacts wirelessly. A timer is cleared, the display is awakened from sleep and cleared, an FTP running message is shown, along with the IP address. If the FTP library is not found in the system modules, then it's dynamically imported. Otherwise, if the library is already loaded, then the FTP server method is called. Either condition starts the FTP server, which will block operation until the FTP client disconnects. When the program resumes, the display is cleared and put to sleep. A function called timer callback will fire when the hardware timer times out. The OLED display is cleared, put to sleep, and the timer is deinitialized. A function called Parse Caller Id decodes and processes the broadcast messages from the caller ID device. Messages less than 20 bytes are skipped because they're not valid or relevant. The 21-byte message header is removed. Then the bytes are decoded to a string. The space-delimited data is split into a list named called data. Filter is used to remove any blank entries. If called data does not contain an entry for the phone number, then the function exits. A try statement wraps the parsing to gracefully catch any errors. The caller ID hardware monitors both incoming and outgoing calls, but only the incoming information is germane. The outgoing is ignored. The indicator field indicates S for start of call or E for end of call. However, the caller ID device has a blocking feature that, if enabled, returns a B at the start of calls that are on an internal list that can be configured as block or bypass. Originally, I was just going to create a caller ID system, but this is a great feature that can prevent all unapproved phone calls from even ringing any of the phones in the house. Therefore, the message can be skipped if the indicator does not equal B, because those will be handled by hardware blocking. Several console print statements are included for debugging purposes only. The caller name is not always included in the caller ID data, but if it's present, then it's stored in a variable called caller name. There can be more than one name provided, so a loop captures any additional names. These names are only for debugging. The actual name displayed on the OLED will be returned from the contacts dictionary. The timer is cleared, the display is awakened and cleared. If the caller ID phone number is found in the contacts dict, then the associated contact name is stored in a list called names, which is split on the space to differentiate first and last name. Display name max is called and passed the first name. The name will display on the OLED in a font that maximizes its size. If the contact has a last name, then it's also displayed on the OLED, again using display name max. If the caller ID phone number is not in the contacts dict, then something went wrong with the hardware blocking or the network broadcast. Theoretically, this should never happen, but just in case, a do not answer message is displayed on the OLED. The hardware timer is initialized in one-shot mode and passed the delay duration and the callback function. This will interrupt the program once in 1 minute and run the function that clears any displayed text and puts the OLED to sleep. So even if the program is blocked by a network socket operation, the hardware timer will still fire and ensure the display is cleaned up. If an exception occurs, then any error message is displayed to the OLED for debugging. Here's the main Python function that will run when the program starts. The load contacts function is called to load the contacts from flash storage. A network socket is instantiated. The socket is bound to UDP port 3520, which is used for broadcasting by the caller ID hardware. Blocking is disabled because the Python select library will be used to monitor the socket. An infinite while loop wraps the socket monitor. A variable result is set to the results of the select method, which is passed the network socket. This will block the program operation until network packets are detected on the specified port. Afterwards, any received message is stored in a variable called MSG. If the message equals a byte string that I designated as the FTP command, then the handle FTP function is called, which will enable the ESP32 FTP server. Otherwise, the Parse Caller Id function is called to decode the caller ID data and update the OLED. That takes care of all the software. I've installed a great VS Code extension called PyMaker. It provides access to the MicroPython Repo on the ESP32 and handles file operations. Clicking PyMaker console opens a REPL shell on the ESP32, which is currently connected by a USB cable to my computer on COM port 4. I can start typing MicroPython commands such as import os and os-listdir. This displays the file contents of the ESP32, which only has the boot.py and main.py file, which automatically runs after boot and connects to the Wi-Fi. All I have to do is click Upload, and my project is uploaded to the ESP32. The Python files, the contacts CSV, and the fonts are uploaded. The directory structures are also maintained, so the fonts will be stored in their own folder. After the upload completes, the ESP32 reboots, and a Wi-Fi connection is established. My main.py file also included an import for the caller ID program, so it automatically starts too. The display shows the loading fonts message along with the IP address. The console shows waiting for calls, so it looks like the software is working. Unfortunately, the hardware is not working as expected. The device is supposed to suppress the first phone ring because the caller ID is transmitted from the phone company between the first and second ring. There's also a feature that lets you store up to 50 phone numbers in non-volatile memory, which can be used as a whitelist or a blacklist. Neither of these two features work. The first ring goes through, along with all blocked numbers. The device is manufactured by a company called CallerID.com in the US state of Georgia. I gave them a call but wasn't expecting much help because it's a 7-year out-of-warranty unit that I bought on eBay. But I was amazed at their enthusiastic customer support. I told them what I was trying to do, and the owner of the company got on the phone with me. He was very hospitable and sounded like an electrical engineer. He explained that the ring suppression and the blocking features were options that were not very popular and not often selected. However, he was very confident that I could make the necessary upgrades myself and proceeded to offer a trove of helpful information. It's such a pleasure to speak with a knowledgeable business owner who takes pride in his work. The caller ID box is secured with 2 screws. Looks like all the components on the main board are all through hole and the layout's very clean. There are empty locations for relays marked K1 to K4 with Form C contact configurations next to each of the 4 dual phone jacks. There are also empty spots for 4 transistors marked Q1 to Q4, and 4 empty resistor locations marked R1, R26, R43, and R60, all with 10K ohm values. I assume the resistor limits the current to the base of the transistor, which is used to fire the coil on the relay, which is used to disconnect the phone line to suppress the first ring and also block unwanted calls. The PCB is held down with 3 Phillips screws. The board lifts out and the front cover falls off. The back cover is bolted to a daughter board, which handles the Ethernet. The boards are connected with a ribbon cable. It's a bit difficult to remove because of the close proximity of a capacitor, but once disconnected, the daughter board and back of the case are easily removed. I marked the locations of the line 1 relay, transistor, and resistor. The holes are filled with solder that will need to be removed. Fresh solder is added, which should help the solder flow during removal. My old Heiko desoldering iron makes quick work of cleaning up the holes. I inserted a 5-volt Hasco relay. Masking tape is used to temporarily secure the relay during soldering. Looks like a good quality PCB, which makes the soldering very easy. Next, an NPN PN2222A general purpose transistor is inserted into the board. The pins are bent to hold it in place during soldering. Afterwards, the leads are clipped flush to the board. Finally, a 10K ohm resistor is added. The pins are also slightly bent to hold it in place. The leads are soldered and then clipped flush to the board. That should take care of the upgrade for the first line. I'll solder the other lines off camera. Unfortunately, the hardware is still not working. I can hear the relay firing, but there's still no suppression or blocking. The relay is just an electromagnetic switch that either connects or disconnects the phone line, depending if the coil is charged. After comparing the wiring diagram to the PCB, I found a trace bypassing the normally open side of the relay, so regardless of the state of the relay's armature, the phone line will always be connected. It's necessary to cut the trace for the relay to function properly. I desoldered the relay on line 1. A tungsten carbide scribing pen is used to cut the trace on the PCB. Afterwards, a multimeter is used to check that there's no longer any continuity between the 2 relay pins. Everything is back together, and I'm calling in from my mobile. The first ring will be from the speaker on my mobile. The relay clicks, preventing the house telephone from ringing. The approved caller name is displayed, and then the house telephone rings. If the caller wasn't on the approved list, then the house telephone would never ring, and the call would eventually be answered by the phone company's voicemail, which can be emailed to a family member just in case it's a valid caller. The hardware timer should clear the display in 1 minute. I'll run the elconfig program that comes with the caller ID hardware. It detects my deluxe caller ID unit listening on port 3520, which you can change along with the network addresses. Clicking Retrieve Toggle displays the operational settings designated by upper or lowercase letters. For example, the lowercase u enables the blocking or passing relay, and the lowercase k designates that all numbers not on the internal phone list will be blocked. This program can also be used to edit the phone numbers stored in the non-volatile memory. I'll type the letter F and click Send Command. A question mark is returned because F is not recognized as a command by the hardware. However, the Python program running on the ESP32 recognizes the broadcasted F command and starts the FTP server. I hope you liked this video. You can support this channel by subscribing, leaving a like and sharing. Thanks for watching.